So carrying on with the 2018 Oxford PAT, we've completed the multiple choice lot. We're now on question 13. We got a network of capacitors. Okay, all capacitors have the same capacitance C. Assume they combine as follows. That's just going to be your resistor rules, isn't it? And yeah, so it's resistors backwards. Find the total capacitance. So if we've got two in series, that's going to be like having two resistors in parallel, etc., etc. So that is going to be C over 2. Then we've got a 1 and a 2, so that's going to make a 2/3 of C, and then we've got 3 adding up to get 3C. So we're going to have 3C plus, well, let's put these over 6. So 3 over 6 plus 4 over 6C, so that's 7 over 6, so 4 and a 1/6 C. That was pretty straightforward for starters. There was a lot of working out space there. Right. Oh, the logs question, always good. Oh, we got different bases. Right, yeah, people get really funny about having logs in different bases. And I know I see people pull out some weird formula that I can never remember, but I don't know why they want to bother remembering all this. Like go into some kind of meltdown over just doing basic logs. So if you've got log base x of 25 equals log base 5 of x, well, let's do our usual log rule. So x to the power of log base 5 of x has got to be equal to 25. Now let's log base 5 both sides. So we can do log base 5 of x to the log base 5 of x is going to be equal to 2. Then we bring the log base 5 down to the front. So we've got essentially log base 5 squared, because we're going to have log base 5 of x multiplied by log base 5 of x is equal to 2. So log base 5 of x is equal to root 2, which means that x is going to be 5 to the plus or minus root 2. There you go. So why you need all this weird stuff with a formula and all the rest of it, I don't really understand. There you go. Anyway, so that's that one. Then we've got, my word, there's a lot of text in this one, but they're all little bits. So I think the biggest trouble I'm going to have here is fitting things on the screen. The car is initially stationary. Time t0, I'm going to put a few things down here. It starts to move at speed v1. So at t0 v1 for a time delta t1. Immediately after this, moves at speed v2 greater than v1 for delta t2 less than delta t1. Okay, after this it's then stationary before. So we've got v equals 0, then we've got all of that. This is going to be a chance to move down a bit. And then we've got v is 0 again. Use this information to sketch a graph of speed against time. Label all axes sufficiently so that the graph is quantitatively accurate. So we're doing a VT graph. Okay, so that's about as big as I'm going to be able to make it on here. We know these velocities we can put down as being positive, so we don't have to worry about a negative axis. So we're stationary until t0. So we need that to be our t0. Then we go to v1. So it steps up here to v1. Then what happens? That's for a time delta t1. Okay, let's scroll down a little bit more so I can put these labels on. So this is going to be at t0 plus delta t1. Then we're going at v2 is greater than v1. So we've gone up to v2. But we're doing that for a shorter amount of time. And then we go to stationary again. So this is going to be t0 plus delta t1 plus delta t2. Okay, a little bit squidged in, but yeah, that's fine. From your graph, determine the average speed, VT, of the car while it's moving. Express VT as a formula using all those symbols. Right, it's known as a time-weighted average. So, okay, we just need to work out what that is. So we're getting the average, well, it's the distance over the time is what we're trying to do here. So we've got distance over time. So this is our, what did they call it? VT. average velocity time weighted. Right, okay, so that's what we've got. So that is our distance divided by our time. So that is going to be, we've got a V1 multiplied by delta T1. We got a V2, this is just working out the areas, times delta T2. And then the total time is delta T1 plus delta T2. So that was that. That's the time weighted average. Okay, compute the numerical value given those. Right, so we've got V1 is 1, delta T1 is 2, plus 2 times 1 over, was it 3 in total? So we've got 2 plus 2 over 3. 4 over 3 meters per second. Right, that's good. Which part of that have we done? That's B. Now draw a speed versus distance graph using the numerical values for speeds and times given in section B. Okay, using all those numbers. Right, so now we're doing speed against distance. Right, so we've got, well, I'll still call it V, so an S for distance, say. So now we're going, what we got? Speed against distance. So we're going at, what was it? 1 meter per second is what we're starting at. So we're starting at 1, and we're doing that for the first 2 seconds. So up to 2. And then we're going at 2. So we jump up to 2, and we do 2 meters per second for a second. So we go then, well, it's 2 again, up to 4. And then we're back down to 0 again. Yeah, that's labelled everything, isn't it? So what did they do? Want anything else? Label the axes as before, do all that. No, that's fine. From the second graph, find the average speed Vs, known as a distance weighted average. Again, express all of those sort of things. Right, so our distance weighted average is going to be, well, the area of that thing, which is going to be equal to, oh, except we're doing it, are we doing this with numbers? We are actually writing out a formula again. All this scrolling up and down. So yeah, we do it as a formula and then give a numerical value. Right, okay. So we're working out this thing again. So we're going to have that we've got, what have we got on all of this? We need to divide by the distance, which is going to be 4. Am I getting this right? Yeah, so the 4 we do have to use. We're doing this in terms of V1. Oh my word, okay, right, no, we're doing something different. I was starting to put numbers in already. So we need to have V1 delta S1, V2 delta S2. Right, okay. So it's going to be V1 times delta S1 plus V2 times delta S2. Okay, so that is, oh, and then we've got to divide it by the total distance. Divided by, because it's weighted by distance, plus delta S2. So actually that's going to look exactly like what we wrote down on the first one. All we've done is change over T's to S's. Right, and then put the numbers in, which were, well, what have we got? 1 times 2 plus 2 times 2 over 4, which is 2 plus 4, 6 over 4, 3 over 2 meters per second. Right, the hardest part of this question is being able to read the questions and look at the answers. Right, that part was a bit more tricky. Which of the two averages, time weighted or distance weighted, is equivalent to the conventional definition of average speed, which we assume to be total distance travelled over total time taken? Well, that's what we just called it here. So that for E is that. That's what we want our answer to be. It's the VT. That's what we normally do. We never do this weird distance stuff. State the mathematical operation that should be applied to the curve of V of t, so the top one, to compute the average speed if we assume v to be any function of time of distance. Right, okay, well, we're going to integrate it and divide it by the time, because that's what we've done here. This is the area divided by the time. So yeah, so for f, we're saying we want to integrate and then divide by time. Then divide by time. Okay, that was quite a fiddly sort of question. Not that bad though. Consider the cross-section of a pencil where a concentric circle of radius r sits at the center of a regular hexagon. If the black area is a quarter of the total area of the hexagon, what is the length of the dimension x in terms of r? Right. So we've got the area of the hexagon is going to be equal to 6 triangles, 6 equilateral triangles. So that's going to be 6 times the height times half the base. So half the base, well, we know that x tan, actually, so opposite is going to be that angle then. So that's going to be 30. So x tan 30 is going to be half the base. So that is x over root 3. So that gives us, well, 6x squared over root 3. I'll leave the root 3 there for the moment. And that was equal to what? That was equal to 4 lots of the black area. So that's going to be equal to 4 lots of pi r squared, because yeah, we've got a diameter of 2r. And we need to get x in terms of r. Right, okay, so x is going to be equal to, well, we're going to have the r on the outside because we're square rooting it. We're going to have a 2 root 3 pi and then a 3 on the bottom. So that was fine. Maybe I'll do one more in this video. Oh, it's a 7 marker. To which order should you expand that in that integral so the approximate integral agrees with the exact result to better than 10%? Well, let's do the exact one first then. So exact is going to be, well, integrating it is relatively straightforward, isn't it? Because we're just going to have a tenth of 1 plus x to the 10 between 0 and 0.1. So that is going to be equal to a tenth of 1.1 to the 10 minus 1. Just as well, they've given us calculators. Right, so I'm going to have to type that into the calculator because, yeah, if we were trying to do that on any of the other papers, that wouldn't be much fun. That has come out at, what is it, 0.15937. So now let's get an expansion then of this. So well, I'm just going to keep adding on terms until I get within that amount. So what are we going to get? We're going to get 1 plus nx. So we have 1 plus 9x. Let's start with these. So as we integrate these, because we've still got to do the integral, that means we're going to get x. We're going to get 9x over 2. The zeros we can just keep on ignoring. So, and we're putting 0.1s in. So we'll have a 0.1 there. We're going to have, what's that, 0.045. So as we're adding them up as we go along, we get that. Then we get 0.145. Okay, so, well, that's already inside, isn't it? Isn't that already inside 10%? Yeah, because if we take, yeah, it is. Yeah, because 10% of that is going to be 0. We're coming from below on this. So we want to do, take off that off of all of this. So that is going to be a 4 below. So yeah, oh wow, so we've already hit it after 2 terms. So that is just it. So we just need to, what does it say? We need to go what order? So it's just first order. I really thought we were going to have to go further than that and do at least the next one. But that was it. Just build them up as you go and move along. Right, so that's another batch anyway. I'm going to leave this video here. Back in a minute.